to run this code by the end of this episode. 2 milliseconds to run factorial.duck. Stupid design, inefficient design, I don't know, but 33, let's call it 33 milliseconds to run the exact same thing in Python versus 3 milliseconds. So that's... Hi everyone, Greg here. And we made it. We made it to a new milestone of 512 subscribers. In fact, we are at 551 subscribers at the moment of recording. So thank you. Thank you very much to all those who did subscribe. If you're watching this, you haven't subscribed yet, please do. And it's really helping the channel, grow and getting the word out there to more and more people. So for the first subscriber special, when we reached 256 subscribers, I created this new programming language. I called it duCx, right, for dumb C, so duCx. And today I'm just going to further develop the language. Now it is still a mock programming language. It is still something that is not meant to be taken too seriously, but it's just a bit of fun and hopefully educational as well. And you'll see how I create this interpreter for duCx. So the goal of the first episode was that we would be able to run a hello world program. So we did that, and we did just a little bit more than that. We are able to print numbers on the screen, things like that. The goal today is that we can run factorials. Okay, we can actually compute factorials in the language. So when you learn how to code, probably the first thing you learn is a hello world program, and then the second thing you're gonna learn is likely to be either Fibonacci or factorials. So we're gonna do factorials here now. So in case you're not familiar, and you probably are, but just for the heck of it, in case you're not familiar, the factorial of 5 is 5 multiplied by 4 multiplied by 3 multiplied by 2, and then you can also multiply by 1 if you want to. So basically, for any integer n, you multiply with all the numbers from 1 through n, right? The factorial of 0 is 1. That's true by definition. The factorial of 1 is 1. And the factorial of negative numbers is undefined. So we're really going to have a bare bones application here. We're not going to do any polish. It is going to be a rough and ready. We just want the language capable enough so that we can actually compute those factorials. So modern interpreters today, what they do is they really do some kind of semi-compilation, right? So they go through the entire code, and then they convert that in some kind of intermediate representation which can run very, very quickly. And that intermediate representation is typically called bytecode. So basically you have those different stages where you load the program, you parse. So parsing basically means you go through a text systematically and you load it into memory in a structured fashion. So the result of the parsing is that you end up with some bytecode, and then you run that bytecode, right? And so I was thinking, if I'm going to do this right, I really have to implement some bytecode, and if I'm going to do that, I better do it early on. So this is the first step in this video. I'm going to implement bytecode. Then the next thing I want to do is I want to implement the while loop. We're going to need some basic control structures in order to make this, in order for us to be capable of running those factorials. So let me show you what the plan is. So this is hello.duck. This is what we left off with at the end of the last episode. So we could run the hello world program here. We could print errors. We can print any string we want, and we can print integers. So that is where we left off. And so it's basically hello world with just a one or two features extra. And this is what I want to run today. So now we can run hello world, we compute factorials, we have some integers, we have a while loop, we are going to parse some mathematical expressions here, and then eventually display the result, right? So that should give us the factorial of 5. So I want duCx to be able to do this, to run this code by the end of this episode. Okay, so I want to start by showing you the files I have in this directory. I have the main file, I have tc.h, that's the terminal control, so I have a whole video just about that, and I've talked about that in the previous episode, so I'm not going to go over this now. And then I have technical. Now those are basically boilerplate functions. They deal with loading content from a file, string manipulation functions, those kind of things. In the previous episode, they were all in the main.c, and I decided I just would unclutter this file by putting them here separately. So that's all that's going on here. So now I have to compile this. So -c to only compile and not link or anything. And now we have this .o file here. And now I'm going to create an executable called duCx, the main.c, technical.o, and then the terminal control needs the threads, pthread. So you see a couple of warnings, you can just ignore those. And now I have my duCx executable here. So let me show you the code. So again, in this first phase, all I want to do is implement bytecode, right? So rather than executing straight as you parse, instead we have this intermediate step where we produce bytecode. That doesn't seem like it's going to make much of a difference now, and in fact it doesn't, but this is just an important step towards the future in order to make sure that as the language continues to evolve, it's always running really fast. So I have this new enum here, up type, so operation type. So the various lines within the bytecode, they're all going to have a type like this. So here a new struct, the loc, LOC line of code. And here it is. So basically the bytecode is going to be an array of this, right? So you have the type here, you have the operator, which is basically a link to the function. And then various variables that are passed on to the function, and a return value. So every loc is going to have a return value, and it's stored here. ID. Now the original idea behind this was that every loc was going to have its own number. So I was just going to number them 1, 2, 3, and so on, such that when there's a jump in the code, so let's say you have a while loop, and if the condition is not met, let's say, and you jump over the while, then there would have to be a pointer to another line of code, another loc. And I was thinking, well, I just number all the locs, and then there'll be something saying, okay, if after the while you jump to loc 20 or whatever. So every loc was going to have its own ID. Eventually, I decided I was just going to use pointers to the loc. It's much better, much faster. So ID here is not actually doing anything. Now you might wonder, then why do I not just get rid of it? Well, actually, first of all, I might use it at some point in the future. I have 32 bits here to do with what I want in the future. I don't know yet how the language will evolve and whether I'm going to need that at some point. But the main thing is that what is very convenient about this loc is that it is 64 bytes long. And 64 bytes on many systems is a cache line. So basically what happens when your CPU wants to get data from the RAM, it is not going to get this 1 bit at a time or 1 byte at a time. It's going to get this 1 cache line at a time, and oftentimes a cache line is 64 bytes. So to have a loc that is just fits nicely into a cache line, it means that for every time that data is transferred between the RAM and the CPU, it gets exactly 1 line of bytecode, which makes it very convenient and very efficient. So the fact that it is an interpreted language rather than a compiled language is going to have its performance cost, but we try to do whatever we can in order to make it run as fast as possible. Creating the bytecode in the first place is part of that, and then making sure that every line of bytecode is a convenient size that is going to be transferred efficiently between the RAM and the CPU is helping matters in order to make it as fast as possible. So that's what this is. And then loc long is exactly double the size. It is 128 bytes. I am not using this currently. In the future, we can have functions that take up to 11 arguments. So, but currently not in use. Here we have the main struct duCx. So I don't like global variables. In fact, this variable list is going to be in a future version. It's going to be inside of that. So we have a block, which is basically an array of locks. So the entire bytecode will fit into that. An instruction index. So that's basically to keep track of where we're at within the block as we're basically parsing the code and producing different lines of bytecode. Here now you can see a clear separation in the code between the parsing functions and the bytecode functions. So basically this will parse the code. Each one of those functions is going to produce its own line of bytecode, and then here those functions are going to run that bytecode. Those functions here are basically all functions you have seen in the previous version of duCx. So now we get to the main function. So here again we have some boilerplate. It's just check that you actually passed on an argument, you passed on a file name. It's loading the contents of the file. It's allocating memory for the main struct. It is initializing it. It is skipping over that shebang line. And now it's just parsing the code, producing the bytecode, and then actually running the bytecode. So you see that here actually we have a very clean main function. So parse code. So because in hello.duck now we only have basically two types of statements at the moment. We either have a function call or we're going to declare a variable. So here the token type is going to be either a function name or it's going to be a data type. And if it is a data type, we are basically creating a variable, right? So here we create a variable. Otherwise we parse the function. Well, the function here is duck parse function. Basically we check, is it a print string, print error, any of the built-in functions. If we get to here without going through a return, then it's a function we don't know about and we don't currently support. So here basically we have the parsing of each one of those functions. So we get the next token. So what happens is once we realize we're in print string, we get the next token, which is basically that string. We check whether the type of token is what it should be, so either a string or a variable name. Then we get the next line of code, the next lock in that block type. It's going to be a function that takes up to 3 arguments. Operator is going to be a pointer to that function, exec print string. And we continue to fill in this lock depending on whether we're dealing with this variable name or with a string. The instruction index then has to be incremented so that next time we call a function like this, we basically get the next line, the next lock within that block. So print in, very similar kind of thing. Print error, very similar kind of thing. And then we can actually run the bytecode. So first the lock, we get the first line in the block. While L type, so the block will be initialized to 0. So as long as L type is not null, there is going to be a line of bytecode that we need to execute. It's going to be either a function that takes 0 arguments or that takes up to 3 arguments. And then here, this one is not implemented yet. This is just a taste of what's to come with the integer addition. I'm not even sure if that works at this point, but this is going to be much better developed in the next version of duCx. So let's not worry about that just now. And then we increment L so that we get to the next line in the bytecode, and we just do this over and over again until we encounter null. So when we do encounter one of those functions, what we do is we take that pointer to the function and we call it. And we call it with basically an argument, which is going to be that string, and then some place to store the return value, which is another part of that bit of bytecode. And then some way of storing the return value, which is another part of that same lock. Right, and so here we have exec print string, and we just output to stdout, which is 1. So write is a syscall. This is what's actually outputting things to the terminal. So stdout, so we just take the value of the string and the length of the string, and we just output this. and it's slightly different whether we're dealing with a variable or a constant. Print int, very similar, except that here we need to convert the int to a string before we can output. Print error is very similar, except that here we have some escape sequence in order to make sure that the error is displayed in red. That's all this really is here. And then duck next token, those functions basically you've seen in the first episode of ducks, and they are for the most part the same. So now if I actually run this, I do hello.duck, and you see it's all working. And let me maybe make this into like a proper Hello World program, and this is basically all clutter. So you see this is basically a normal Hello World program, and you can't tell much of a difference now because the changes that we have made, this bytecode, are basically all changes that are just occurring under the hood, but those are changes that are important towards the future of the language. Right, so now I made the changes to ducks, which allow both for the parsing of the while loop and the parsing of the arithmetic operations. So if I compile again, and again ignore the warnings, now what I can do is I can run this file factorial, and now you see this is actually working. We have computed our factorial, and the factorial of 5 is indeed 120. So let me show you how I did that. So in this file now, there are a lot of changes. First of all, block. I just made the block bigger, right? So let me show you here. This is the main struct of ducks again. So this block, I just have more. I have basically a longer array, and I didn't hard code the number of locks. It's now this macro. And vlist, I said I was gonna remove the global variable, so vlist is now in here as well. So the uptypes, we now have a lot more of them because ducks is now a lot more complicated. It allows for a lot more things to happen, so a lot more uptypes. So here again in this main struct, we have another array, and this is an array of lock pointers, and it's CSP, so control structure pointers. So keep track of the nested control structures. So what happens here, when a while is going to be processed, there will be a lock for this while. If the condition is not met within that lock, it needs to know where to jump to. So what will happen is it will parse the rest, and then it will get to this. That is the point where the parser figures out, oh, this is where you need to jump to if that condition is not met. So at that point, it needs to be able to go back. So the first while, there will be a pointer in this array. When it gets to the closing curly bracket, it will just look in that array, and it will look which while that corresponds to, right? And it's a whole array of those so that you can nest the whiles into each other. Okay? Actually, I didn't test that. Now that I think about it, I didn't do multiple whiles into each other, so I'm not even sure 100% if this works. Okay, so let me show you how I did implement this. So we have same thing in the main here, parse code. This is now more complicated, as you can see, but we have duck talk keyword. So while is a keyword. So if we encounter that, we do duck parse function. Now, the thing about this is, as far as the parser is concerned, if you have a function, you have basically a word and then something in brackets. And if you have a while, you have basically a word and something in brackets. So our parser right now does not need to really understand the difference between a while and a function. So that's why I put it in here. So if we have a while, then duck parse while. Okay, this is a function. So you get to the next token. And within the brackets, we do expect a variable name, right? So if the variable has value 0, then the condition is not met. It will skip. If it's any value other than 0, then the condition is met and it will execute the next line within. the while loop. This is very similar to how it works in C. So in C, if you write something like that, what's going to happen is it will take that entire expression, it will evaluate it, and then this expression by itself will return either a 0 or a non-zero value. And then if it returns 0, then this while will not be executed. If it is anything other than 0, then the while will be executed. So we're doing the same thing here, except that we're using a variable, and that's all we currently support. So in the while, you always need to have a variable. So that's what it does here, is just check if there is a variable name. Then it will get the next lock within the block. Now, I did clean that up a bit and made it into its own function, and that function will also take care of incrementing that instruction index. So basically, it gets the next lock in the block, and it will just fill it in. So we have the operation type here is a while. The operand is going to be that variable of which we need to check is the value 0 or not. We fill in that CSP so that we can figure out later where to jump to. We make sure we close the bracket, that the condition is just closed. We look for that curly bracket, this open curly bracket, and that basically that's it for the parsing. So once you get to the bytecode, what's going to happen is, and again here for the bytecode we have a lot more complexity, and I'll discuss that in a minute. But while L type, and then it's going to go all the way down here. And what it would normally do, it would just increment that L. But because now we have those control structures, we can no longer rely on the notion that it will just go sequentially through every single one of those locks, one after the other. So basically here it looks if we have a while operation. If it does, it will check what's the value of that variable inside the while. If there is a non-zero value there, it will just increment the lock and go to the next instruction. So that will bring us inside the while. If that value is 0, on the other hand, then that lock, the next lock, will be whatever operand 2 is, which is the space outside the while that we need to jump to. Now here, L type, duck up, jump. This is where we get when we meet that closing bracket. So if we get to the closing curly brace, then that L will be operand 1, which is basically going back to this lock where we see the while and we assess that condition again. So let me go back to parse code. Get duck parse code. So if we have the keyword, then we process this while. If we find the closing curly bracket, so I call it closing block. Basically this whole thing is also called a block. So if we see closing block, we get that next lock again. We call it a jump. That's the type. If the CSP at that point is empty, that means some mistake happened. In fact, I'm just gonna exit at that point, because what else are you gonna do? Some error occurred there. Otherwise, we just decrease that counter and we look at what is in the CSP at that point. We set that one to no. So what we do here is we take the lock that we're currently processing and we basically say we need to jump to that. So that is a pointer to the lock where that while loop, that while condition will be assessed. And then in the while, the operand 2 is basically L plus 1. So that is the lock just after that closing bracket, which is where we jump to if the condition is not met. Okay, so that's basically the implementation of the while loop. Alright, so now how is duCx going to parse expressions? So it needs to be able to deal with very simple ones. So like if we have this variable n equals 1, or if we have something more complex, like this. So variable j equals variable n plus 2 times 5. Now, not only that, but the operations need to happen in a particular order. So the order of operations is, first you deal with whatever is inside brackets, then you do the multiplication and the division from left to right, and then you do the addition and the division from left to right again. So here we would have 10, and 10 plus 1 is 11. So here j is 11. What if I put brackets here? Now I do this first, so we have 3. 3 by 5 is 15. So what we're going to assume is that there are no function calls in the expressions for now. So if you have a function which returns an int, this is not going to appear in there. In the next episode of duCx, we'll probably deal with functions. And I mean not the built-in functions, but functions that you can actually write as a programmer, and then we'll revisit that. But for now, we'll assume there are no functions in there. So beside the operations, we have only variables and we have constants, and that's the only thing we are going to consider here. Right, so how am I going to solve this problem? Well, basically in duCx we'll have this data structure term. So basically each one of these is a term. So I call the data structure term. And then you can have different values. So you can have a variable, the pointer to a variable, or you can have an int. So all we're considering at the moment is an int, but putting it in a union already makes it easier towards the future to basically allow for floats or whatever other types of value we want to support. Then we have a pointer, a lock pointer, the return value, RET, that's the return value. So basically what will happen is, if let's say we have brackets, stuff will be processed within the brackets, and then it will return a lock pointer, and this will find its way in here. Or there's other cases where we're going to need this. I'm going to show you this in a second. But basically this is the data structure we're going to use to parse those expressions. So how is that going to work? I take my expression here again. Right, and by the time that we get this function duc parse expression, this function, that's all duc parse expression is going to see. So the equal sign and whatever comes before, it's not going to look at that. We're going to have this array of term, right? And what it's going to contain, it's going to contain n plus. So plus is not technically part of the term, it's in between the terms, but nonetheless I put it in the data structure. So that's that operation here. That's going to be the plus or the multiply or the division or whatever, right? So then 2 multiplied, then 5, and then there's going to be a null here. The null, because it's initialized to null, so that it's just going to stay that way, and then the rest of the array will be null, right? What it's going to do is it's going to scan the array from left to right. It's going to do the multiplication first. 2 times 5 is 10, so here now we're going to have a lock pointer, the return value of which will be 10. This will be replaced with a space. Once that operation is performed, it's replaced with a space. It's going to continue to scan the array from left to right. It's not going to find any more multiplications of divisions anymore. So it will start again, this time looking for additions and subtractions. It's going to find this plus now. It's going to look for the next term. It's going to skip over that one because there's space. It's going to find this one. It's going to add a variable n to whatever the result was of this. So that would have value 10 at that point. It's going to replace this with a space. It's going to replace this with a new lock pointer, this time the one which has return value of this operation, the variable n plus 10. It's going to continue to scan the array, won't find any more additions and subtractions, and at that point it's just going to stop. Okay? What would happen if we had instead something like this? Well, we would have a first array of terms. It would have a bracket and a multiplication and a 5 and a null. What would happen is it would recursively call the parse expression. There would be an array n plus 2, and then once that function is done running, it will return a lock pointer. That lock pointer ends up here, and then it does the same thing here. Okay, so this is basically how the parsing of expressions in duCx is gonna work. So let me show you this now in code. Alright, so now let's look at the code and see how I implemented that parsing. So here we have the struct term, which I showed you earlier. And we're gonna go down all the way to the main function here. So we have parse code, right? We have the same thing over here. So we're parsing the expressions. So either we're gonna have a declaration, variable name, an equal, and then some expression, or we're gonna have a variable name, an equal, and then the expression after that. So here, if the next token is a data type, in here we're going to parse an expression, or if we have a variable name, in here we're going to parse an expression. So duck parse statement. So we're in this case here. So that token will contain the variable name. So we pass on the token to find out what the variable is. We get the next token. We see if it's an equal sign. If it is, if it's not, then something went wrong, something we don't understand. And by the way, I think it's a good idea to force the programmer to always initialize the variable. So even when you declare a variable, I always want to see an equal sign there and always at least some value given. So if there's an equal sign, duck parse expression. Okay, that's where the real bread and butter is happening. Right? We pass on the main duck struct, we pass on the token, and we pass on the level. I'll show you in a second what the level is about. This will return a lock pointer, and then operand 1 will become v. So basically we process an expression here, this returns a lock pointer, and then we'll say whatever the result is, we just assign it to that variable. So operand 1 becomes that variable, so that's going to be $result here. Things are getting assigned here. So parsed expression is here. This is the level. The level is basically how many times you nest brackets. So we're not going to allow people to nest brackets within brackets ad infinitum. At some point you've got to stop. So 63 levels, which is of course a lot more than is reasonable, and you never want to nest that many brackets. However, I think that number is more or less in line with what the C standard does allow, so that's kind of what I went for. So if we have more than so many nested brackets, we just kind of raise an error. So we start with level 0. Here we have our term array. So we can have up to 63 terms. Now, of course, when you consider the terms within the brackets, you can really have more than that. Initialize it to 0. Term index. So as we do our operation, our addition, let's say we need 2 terms. So this is going to point to the first term, and this is going to point to the following one. So while we're not encountering a delimiter and while we're not encountering close brackets, we'll look at the next token. And of course, since we recursively call this function, when we do encounter brackets, when we encounter the close bracket, like we're done with that level, and then we just need to return, and we kind of go one level up, so to speak, and we kind of go back high level in the expression. So what if we encounter an open bracket? This is where we recursively call duCparse expression, level +1. It will return the lock pointer, and that's going to be the return value for that particular term. We look at what's next. So after the brackets, do we have a plus or a multiply? Do we have any kind of math operation? Or do we have a delimiter? Or we could have a closed bracket, so we could have brackets within brackets, and as we've finished processing those brackets, then we encounter the closing brackets of like a level up. So in that case, we need to return as well. Ti +1. So basically what we're doing here is we just filling up that array here. Okay? So in the first loop, we're going to fill up the array. And then in the next loop, we're going to scan for the multiplies and the divisions. And then in another loop after that, we're going to scan for the additions and the subtractions. So this is if we encounter brackets. If we encounter a variable name, right, we just fill in that T array accordingly. If we encounter a number, then we fill in that term accordingly, and same thing here again. So we do this until we encounter either the delimiter or a closed bracket. If we didn't find a term, something went wrong. Maybe we have brackets with nothing inside, or maybe there's just nothing after that equal sign, or something isn't right. If Ti = 1, then we're dealing with a simple assignment. Right, so we have a single number, or maybe we have a single variable. Alright, so if we have something like that, then either this kind of situation or this, Ti would be = 1. Even if we had brackets and maybe some complex expression in here, one level up, we would then have only the brackets, so we would still have Ti = 1. So if Ti = 1, we're dealing with a simple assign. So we're talking about here, this is something that we will encounter in the enum of the operations. So we assign an integer, and this has v. V for variable. So if I go all the way up here, the operation types I have here assign _L, assign _V, and assign _C. So that's a constant. So if you have a 5 or a 7 or whatever, a V for a variable name, and then an L for a lock pointer if you have the return of a more complex expression. So L, V, and C, that's a pattern I've kind of used consistently with the different operations. So L type, I start with the assumption that we assign a variable. If that turns out not to be the case, if in that term what is actually filled in is a return value, so the lock pointer, we're going to do type, we're going to decrement 1, so that's going to change this type to assign L. Right? And then if it turns out that it's the variable that's filled in, then we don't need to do anything in particular with that type. If it turns out that it's the I value, the constant that's filled in, then we increment type by 1, and that will get us to assign underscore C, so with the constant. So that is if ti equals 1. Otherwise, we're going to have at least one mathematical operation that we need to perform here. So we set ti to 0. And while we are going through every single term in the array until the operation is null, and so then we know we have encountered the last term, what we do is we look for multiplications or divisions. If we do, then we figure out what ti next is going to be. So that's the term, the other term we do the operation with. We skip over all those that have this space. And then we actually produce a bytecode, so we get the next block pointer in the block. If it's a multiplication, we just have the operation type will be multiplication. We assume it's a variable. We multiply a variable with a variable. And then here's where we do something very similar to what we did with the assignment. We check what are we actually multiplying with. We adjust the type accordingly. So for the first term and then for the second term, ti next.return is L. Right, so that's where I actually stored the lock pointer in the return value. And then the operation for the first term is set to a space. Right? And then we do ti plus equal 1. So we just go through the next bit of the array, look for another multiply or divide, and we go through the array until encounter the operation that is null. And after that, we do the exact same thing, except we do it for the addition and the subtraction. And this is basically the same thing. Then we return L. So maybe I can demonstrate that this works with more complicated operations. So if I'm just gonna make something up here. Okay, so if I were to do something like that, so 5 by 5 is 25, 1 plus 25, 26, 23, 23 plus 1, 24. So if I execute this, that should give me 24. And then here you see that indeed it's printing 24. Okay, so one thing I can say about duCx already, and I didn't think I would get there as soon as the second episode, is that duCx is Turing complete. And I think that's really awesome. Now, what is Turing completeness? Well, it means that duCx can basically compute everything which is computable. Right, so every single algorithm, every single thing that can possibly be computed, duCx can do it. So there are a couple of caveats here. In 1937, when Turing first published his paper, he conceptualized a device which would read and write from a tape, and that tape was an infinite tape. So in other words, he assumed infinite memory. And obviously that's not the case with duCx. We have 1024 locks. We have up to 127 variables, so we're quite limited here. But those caveats notwithstanding, we do actually have achieved Turing completeness, and this is really great. So all you really need for Turing completeness is being able to perform all the basic arithmetic operations, and you need the sequence, the selection, and the iteration. So basically the sequence means you can perform one instruction after the other. The selection is basically the if, and then the iteration is the while. So there is a proof called the Bohm-Jacopini proof that demonstrates that if you have those things, if you have those three elements, the sequence, selection, and iteration, then sure enough, you can perform every single algorithm. So now you might say, we only have the while loop with duCx, we don't actually have a selection, and so therefore, is it really Turing complete? Well, yes, we can actually perform a selection within ducx even without an if. So if you consider the following pseudocode, so if a not equal to b, then perform x. How would you do this in ducx? Well, you create a variable and you take the difference between a and b. If a and b are the same, then the difference would be 0. Then you just do while diff. Straight away you put diff to 0 so that the loop executes only once, just like an if, and then you perform x. So obviously that's not a very convenient way of doing it, but the point is that it is possible, and so therefore it counts as Turing completeness, even if it's not very practical. Similarly, when you want to do this other bit of pseudocode, if a equals b, right, so now you're checking for the equality of a and b. How would you do that? Well, this is even more convoluted, but you look at the difference again. You assume that they're the same with a separate variable. So then you do while diff, which is basically testing that assumption. If that assumption is wrong, in other words, if there is a difference, then you set same to 0, and then you do while same. And it's a very similar thing. It's just a bit more work and more convoluted, but basically it works. And we do have a selection, and so basically we have over 3 components: sequence, selection, and iteration, and that gives us Turing completeness. Okay, so the last thing I want to do now is a speed test. So this is just for a little bit of fun, now that we can actually do something more meaningful than just a hello world program. I want to compare the different programming languages with each other. So here we have the same code, or at least as similar as they can be, different programming languages permitting. So I'm just going to show you all of those bits of code. So basically what I do in ducx, I compute the factorial of 12. That's the largest factorial that you can compute with a 32-bit integer. So here it is. That's very similar to the code you have already seen earlier. This is the same code in Python, so there's nothing fancy here, and I don't normally write in Python, so I'm not even claiming this is particularly good Python. But the point is, it is as close to the ducx code as I could get it. Here we have PHP, very similar kind of deal, and here we have Perl. Alright, so they're all the same. And here we have it in just plain C. So what I want to do is a very simple speed comparison. So I'm just going to compile this and let me run this one and see that it works, right? But what I'm going to do is I'm going to use the time command, and this will allow me to basically see how long it takes for it to run. So I'm going to do time factorial.duck. Let's begin with duck. And so when we run this, it took 2 milliseconds. 2 milliseconds to run factorial.duck. Right? Now I'm going to do this 3 times each time, so that we get we can kind of take the average of the 3, and we don't get the same result every time. So you see now it's more like 3 milliseconds. That's how long it takes to run that duck script. So now let me do it with Perl next. So before I run this, I do need to say that this is not an entirely fair comparison. The reason being, Perl and the other, they are full programming languages, whereas ducx, while it is Turing complete, it is of course very, very deficient in features. And so basically, you know, we're not really comparing apples with apples here. But anyway, let's just see what this is. And okay, so I'm going to do it 3 times every time, and I don't know what happened here. But basically, it takes, let's call it 6 milliseconds, right? And I do it a 4th time here. So it's between 5 and 6 milliseconds to run the Perl interpreter. And it's between 5 and 6 milliseconds to run that same script, exact same script in Perl, okay? So now let's do the Python. Well, yeah, let's do the Python script. And what have we got here? Again, it always takes a bit longer the first time, but you see the sheer absurdity of, you know, modern programming languages and all the bloat and all the crap that you have nowadays. Is it bloat, or is it just stupid design, inefficient design? I don't know, but 33, let's call it 33 milliseconds to run the exact same thing in Python versus 3 milliseconds. So that's 11 times faster, right? duCx is 11 times faster than Python, and that's really ridiculous. And again, duCx doesn't have all the features, but still, it's like Perl was only 6 milliseconds or so. So, you know, that tells you something about modern programming languages. So now let's have a look for PHP. So yeah, let's ignore the first time again, and okay, so 35, 36 milliseconds for PHP. So it's almost like modern languages are inspired by each other's mediocrity. It's like, yeah, well, I mean, I don't know what's going on here, but this is ridiculous. And when we look at the compiled versions of the actual C code, 3 milliseconds, right? 3 milliseconds. So that means that duCx, while it should be slower, an interpreted language, while it should be slower than a compiled language, it is not noticeably so. So I think that's really incredible. And yeah, I mean, what do you think of the fact that PHP and Perl are sorry, PHP and Python are so much slower? And again, this is not a very scientific test, or not a very advanced test or whatever, but still, I think it's very telling. They don't make programming language like they used to anymore. Okay, well, look, this is it for this episode of duCx. I hope you enjoyed. I hope you learned something. Thanks again for 512 subscribers. And if you want to see the next episode, make sure you subscribe. Make sure you get me to 1,024 subscribers. That would be really awesome. And in the next episode, I'm going to implement functions. So you're going to be able to write your own functions in duCx. I'm going to have to implement a stack. So we're going to talk about a stack, and we're going to have to talk about scope and all of those kind of things. So that's probably what I end up doing in the 3rd episode of duCx. So if you want to see that, subscribe, share, comment, like, all the good stuff, and just help me along to grow the channel. So thank you very much, thank you for watching, and bye now.